Hi. So this is the second video in a series of 3 videos about how you can compile regular expressions, regex patterns, in other words, by using an adaptive radix tree. Now, full disclosure, I think I might be the first person that's done this with an adaptive radix tree specifically. So I think that this is not new with tries in general. I know that there is this concept of a trie regex pattern, but I admittedly I did not look too hard, but from what I could tell, I didn't see any implementations of adaptive radix tree. I didn't see anything in the literature about compiling regexes with them. And so I just want to share what I think it might be a novel approach. Maybe it's not, but it's a cool tree traversal technique for producing a regex pattern. So in this video, we're going to go through how you can walk your tree of your adaptive radix tree and produce a logical representation of a regular expression. Okay, this type of regex is going to be called a trie-regex or a trie-style regex because it's going to have these shared prefixes kind of abstracted away, as we talked about in the last video. So before we get started, I just want to say this: I'm doing this with my adaptive radix tree that I implemented in JavaScript. You could do it probably with a lot of different adaptive radix trees, but I want to say there's one property that the adaptive radix tree must have in order for you to do this kind of thing. So first of all, it's very common for adaptive radix trees to have some form of path compression or lazy expansion, which are these techniques that make these one-way paths inside the tree or hanging off the end of the tree leading to a leaf node to compress them, okay? And there's various techniques. These techniques could be considered lossy forms of compression or lossless forms of compression, okay? So if these are lossy forms of compression, then obviously you cannot use this technique to compile regex patterns, okay? You need to make sure that if it's using path compression and lazy expansion, your adaptive radix tree is using lossless versions of these techniques. Okay, you need the full one-way paths represented in your tree, or this is not going to work. So first of all, here I have right here called character class. That one I don't actually use, but not non-capturing group and capturing group. Okay, you can see those. Those are two supporting data structures. They're basically just a class. It extends array and it has an optional Boolean flag on it. Okay, so they both behave like an array, but they have different names and they have this optional flag. The third critical data structure that I use in many places in this project, but especially for compiling regex patterns, is this thing called a byte stack. So it's just a supporting data structure. It's a really simple vector type of data structure, which is like an array that can grow. Okay, and so it's it's for byte values. Okay, I'm not going to go over the implementation of it because there's millions probably of implementations of vectors, and there's really nothing new here. Okay, so what I'm going to do is I'm going to fast forward to the function in my regex in my tree called toRegex. Okay, so this is the function that walks the contents of your radix tree. So obviously you need to insert your keys into the tree. Now, your trees have to be binary, your strings have to be binary comparable. Mine, I use a Latin 1 encoding. If your character ranges do not fit in Latin 1 range, then you need to remap. You need to do some remapping or come up with your own collation mapping, okay? This technique with this tree, this can work as long as the alphabet of the strings that you have, as long as the alphabet is not more than like 255 unique characters, okay? If you need to recognize more than that, then I don't know if this is the right tool for you. But for most use cases, that's fine. It's just whether or not it'll fit in Latin 1. And if the Latin 1 mapping doesn't work, you got to do your own remapping. So this toRegex function, you take some arguments. Suffix compressed, that's not something that I actually do, so forget about that. That value is ignored. The second one, capturing groups, false. So this means, do you want the pattern to be rendered with capturing groups or non-capturing groups? Okay. Third, it's asking for sentinel. So sentinel means, what is the sentinel value? that terminates the strings. So in my tree, to support strings that each have the same strings that are prefixes of other strings, I terminate them all with null bytes. Okay, and that's from my Latin 1 encoding. You don't have to use a null byte. You could use a different code point that's reserved for terminating your strings, and so that's what that argument is for. And then any code point, I don't think I actually use that one. So anyways, let's get into it. So the first thing is I am assigning to a value called group here, a constant. If you pass the capturing groups flag, then we're going to use the capturing group class that I showed you earlier. Otherwise, it's going to be the non-capturing group. Okay, and then we instantiate a new group and assign it to the result variable. Then we're going to use a pair of stacks in order to do the traversal. So the first stack, the ART stack, this is going to be a depth first traversal, okay? So these stacks are going to allow us to descend the tree, and then as we go back up, to go jump over, across to the next value for us to descend. You'll see what I mean. And so the ART stack is for having these the nodes, right? Because the adaptive radix tree has node 4, node 16, etc. So these nodes each have iterators, and the iterator, that's what goes in that stack. Okay, so that when we come back up, we can consume the next value of the iterator, which is the next key value pair. The res stack is for the results, so that's so that we can track the position of our traversal in the result tree. Okay. So first what we're going to do is assign the root of the adaptive radix tree to the variable current. And we're going to check what kind of type it is. If it's a node leaf, then that means that there is nothing in the radix tree, so nothing substantial at all. So we can just return an empty string. Now, if it's a node 1, which I'm using a linked list, I'm not using vectors like in the classic adaptive radix tree. So if it's a node 1, which is like one of these linked list values, then what we need is a new byte stack. And then what we're going to do is we're going to push the byte stack into the current result value, which currently is a group, but later on we could reassign other things to it, as you'll see. And we're going to push that byte stack in there, and then we're going to go through and we're going to push the key byte values as long as we're going to keep calling like next basically, right? And we're going to get the child of that node 1. And if that's a node 1, then we're going to take that value. And so as long as we have node 1s, we're going to keep appending the key bytes from those node 1s into that byte stack. Okay, so this is, you can think of the byte stack as like a concatenation sequence of characters. Until and at the afterwards, if we encounter a leaf node, then we're gonna break out of this. Otherwise, by default, what we're going to do, that means that we're not a node leaf, we're not a node 1, so that means we're a higher order node type. Okay, that means node 4, node 16, node 48, node 256. This means that what we need to do is we need to create a new group of alternatives or a new group of options. Okay, and so that's what we're doing here. We're creating a new group, and then we are putting that new group into the result and putting the reference to that in the result stack. And then we're creating a new iterator from that node, and we're putting that iterator into the ART stack. Now we're going to have a while loop, and we're going to keep doing this while loop until the ART stack, until the last value is not null. Okay, and what we're going to do is follow this workflow down here. Okay, so IR is this value where we're taking the iterator off the end of the ART stack, and we're calling next on it. And if the value of that iterator that's returned is done, then that iterator is exhausted, and we pop a value off the ART stack in the result stack. So we go up and we go up the tree, back up the tree once in our traversal. Otherwise, we have a value from the iterator. If it turns out that it's a sentinel value, then we have to do something special. So if we encounter the sentinel value, that means something special. If we're encountering the sentinel value, it means that we need to make the current group optional, because it's like if we want to support having words that are prefixes of other words in the tree, then that means we want to be able to have Tim and Timothy separately in the tree. And so um, when we encounter the null byte, that means that we encounter the terminating null byte at the end of Tim. Okay, and that means that the group of alternatives that has, for example, the oth of Timothy, that needs to be optional. All right, so that the regex pattern can match either just Tim or Timothy. Okay, and obviously we are not putting the sentinel values from the radix tree into the byte stacks. We're not doing that, okay, because regex doesn't work that way. Anyways, so then we're going to move on, and we're going to do kind of a similar logic that we did above, where we are going to plow through some of the node ones if necessary. And so that's what we're going to do, okay, is we're just going to keep descending the tree. If it's a node 1, we just keep on putting values into the current byte stack. If it's a radix tree, if it's a compound node type, like node 4 or higher, then that means that tree, that node represents a group, and each of the key bytes at that node and the values, the tree that's attached to that key byte as a child, that subtree, that represents one of the options, okay, in that group that represents that higher order node type. So that's the key concept. Like, you don't have to actually even do it exactly the way that I'm doing. You just have to understand that's the concept, right? You're either doing concatenation if it's node 1, or you're doing with these higher order node types, that means you're starting a new group of alternatives, and that's really all it is. Now, you at the end, but you can also do additional passes to suffix compress, which means like you could walk the tree, and for each one of these groups, you could chop off like shared suffixes and concatenate those onto the end and compress it even more. I wanted to support that, but I got bored with it. I didn't feel like doing that. And that's it. That's pretty much um, that's pretty much how it works. We return that intermediate result, and that's where it goes. So in the next video, I'm going to go over how the serialization works. See you then.